Look up at the night sky and you might feel a profound sense of calm. An endless dark ocean dotted with light, serene and impossibly distant from the world we've built down here. It would be easy to assume we're sheltered from whatever happens out there. But that assumption is dangerously wrong. Our planet is being bombarded continuously. A relentless, invisible assault of cosmic rays, tiny high-energy particles slamming into our atmosphere, triggering cascades of ionization powerful enough to cripple satellites and fry the electronics we depend on every single day. The real mystery, though, is this. Where are they coming from? For over a century, astrophysicists have chased this question through dead ends, frustrating detours, and unanswered riddles. The origin of cosmic rays, even the type of object that could produce them, has slipped through our grasp again and again. But right now, a revolutionary new branch of research is finally closing in. We are not only discovering what to look for, but what we're finding is staggering in its raw power. What kind of object in the cosmos could possibly generate a quadrillion electron volts of energy? I'm Alex McColgan. This is Astrum. Today, we trace the footprints of cosmic rays all the way to the bleeding edge of known physics. We'll explore how scientists build machines that detect the most energetic particles in existence and uncover a brand new class of astronomical objects, so violent they once seemed like pure fiction. The Milky Way pulses with energy, yet human eyes can perceive only the thinnest sliver of it. Beyond the visible spectrum, charged particles radiate at far higher frequencies, producing X-rays and gamma rays that scatter energetic signatures throughout the cosmos. Astronomers read these signatures like forensic detectives, reconstructing the invisible machinery driving energy through our galaxy. But within this sea of charged particles, one group has stubbornly defied every attempt at explanation. In 1912, Austrian physicist Victor Hess made an extraordinary ascent by hot air balloon, climbing to 300 meters to measure ionization rates in the upper atmosphere, specifically how rapidly atoms and molecules were gaining electric charge. The scientific consensus of the time predicted that ionization would fall off with altitude, weakening as the distance from Earth's surface grew. Reality had other plans. Hess, instead, measured ionization levels 3 times greater than those recorded at sea level. That one result demolished the prevailing theory and opened a door to something far more profound. The radiation he had spent his career investigating was not radiating up from Earth. It was raining down from space. He had found cosmic rays, and they were not here as guests. Our planet endures a ceaseless barrage of them. These high-energy particles, predominantly protons, hurtle through the void at velocities approaching the speed of light before crashing into Earth's upper atmosphere and spawning cascades of secondary particles that wash down onto the surface below. The consequences are real and serious. Secondary particles generated in these cosmic ray showers, including muons, neutrons, electrons, positrons, and gamma rays, interact with living tissue and can drive genetic mutations and radiation-related cellular damage. When they intersect with orbiting satellites or other electronics in space, they trigger ionization events that degrade circuit performance or cause sudden catastrophic system failures. And cosmic rays have not limited their mischief to our technology. They have been confounding our best scientific minds for generations. For more than 100 years, pinning down the origin of cosmic rays has ranked among the most obstinate unsolved problems in high-energy astrophysics. Their fundamental physical properties make tracking them nearly impossible. Magnetic fields warp their trajectories before any source can be traced, and they shatter into cascades of secondary particles before their identity can be confirmed. These challenges crystallize when researchers attempt to map out the cosmic ray energy spectrum. Plotting the number of incoming high-energy particles against their respective energies reveals a sharp inflection point scientists call the knee, beyond which the truly extreme cosmic rays exceeding 4 peta-electron volts become drastically rarer. Some researchers initially theorized that this knee represented a transition boundary, separating cosmic rays born within the Milky Way from those arriving from far beyond it. Others simply had no working answer. Just as the field seemed to be stalling, one extraordinary observatory stepped forward and rewrote the rules entirely. Before we pull back the curtain, want to experience the cosmos firsthand yourself? You might not have a research facility in your backyard, but you can still witness galaxies and the skeletal remains of dead stars, like the Crab Nebula in breathtaking detail through the Dwarf Mini Telescope, the proud sponsor of today's video. Take a look at this image of the Crab Nebula captured by community member Julia Rash, using this genuinely book-sized, ultra-portable instrument. Julia had only a brief window to shoot it after 4 consecutive weeks of cloud cover and an early start the following morning, yet the result is stunning. She pulled it off thanks to the Dwarf Mini's automatic star tracking capability, which locks onto your chosen target with speed and precision, alongside its live stacking function that layers multiple exposures into astonishingly clear images of deep space objects. This telescope has genuinely earned my enthusiasm, and I'd point anyone curious about getting into astronomy straight toward it. Scan the QR code on screen or follow the description link to explore it yourself. Use the code ASTRON5 at checkout for 5% off. Now, let's get back to the search. The observatory about to transform our understanding of ultra-high energy cosmic rays is extraordinary in every sense. The large high-altitude air-shower observatory, known as El Hasso, sits nearly 4,500 meters above sea level amid the mountain ranges of Sichuan Province, China. Its singular objective is to detect the most energetic particles the universe can produce. Leading this mission is Professor Zhen Cao, who sat down with Astrum for an exclusive conversation about the observatory's work. According to Professor Cao, achieving precision measurements near the knee of the cosmic ray spectrum demands two things simultaneously. The detector array must be large enough to matter, and it must be capable of reconstructing the identity of the original particle from the shower it creates. Cosmic rays become exponentially rarer as their energies climb. For the absolute highest energy particles, fewer than 1 per square kilometer is expected to reach Earth over an entire century. To meaningfully detect them, your instrument must span far more than a single square kilometer, which is precisely why El Hasso covers an area equivalent to roughly 190 football fields laid side by side. On the particle identification front, every cosmic ray collision with the atmosphere produces a wide debris field of secondary particles, and scientists must reassemble those fragments to determine whether the original visitor was a proton, a helium nucleus, or something considerably heavier. It's a painstaking reconstruction process, requiring total coverage of the shower's fallout. El Hasso is among the most comprehensively equipped observatories ever designed for this challenge, deploying at least 3 distinct but interconnected detector systems, working in concert to capture the shower and decode the original particle. That unmatched capability quickly delivered a landmark discovery. Professor Cao recalled, "At the time, we only had around half of El Hasso built. We put it into operation for around half a year and suddenly found that there were so many gamma rays. By 2021, El Hasso had recorded gamma ray photons carrying energies above 1 peta-electron volt, or 1 quadrillion electron volts, and one extraordinary photon measured at 4 quadrillion electron volts, setting a new all-time record for the highest energy photon ever detected. To put that into perspective, that's nearly 150 times the energy of the fastest protons ever accelerated by the Large Hadron Collider. Now, the conservation of energy is non-negotiable. Peta-electron volt particles don't materialize spontaneously. That colossal quantity of energy must be transferred from a source to the particle. Scientists had theorized about what such a source might look like for decades. El Hasso's detection proved its existence beyond any reasonable doubt. That source is the pevatron. Pevatrons are any astrophysical object capable of accelerating particles up to a peta-electron volt in energy. Their confirmed existence promised to transform the entire cosmic ray hunt. But how do you actually locate one? Fortunately, El Hasso was far from finished. Gamma rays carry a decisive advantage over their charged counterparts. Being electrically neutral, they travel through space in perfectly straight lines, undeflected by magnetic fields. That gave El Hasso an entirely new dimension of investigative power. It could trace gamma rays back along their paths to the regions of sky they originated from. Mapping those traces across the full sky, scientists identified 12 distinct gamma ray sources producing ultra-high energy photons, several of which showed unmistakable signs of accelerating particles to quadrillion electron volt scales. There was one complication. Knowing the direction of a source is not the same as knowing its distance. 12 lines of sight extending indefinitely through space is hardly a precise address. But scientists had one more piece of information that would dramatically tighten the search. Since the Big Bang, the universe has been saturated with photons, the so-called cosmic background radiation. These photons are extremely cold with characteristically low energies. Ultra-high energy gamma rays traveling through the sea of background photons face a serious problem. At high enough energies, collisions between gamma rays and background photons are highly probable, and when such a collision occurs, the gamma ray is annihilated. This imposes a strict distance limit on how far any ultra-high energy gamma ray can actually travel. If El Hasso was detecting them here on Earth, they couldn't have come from very far away. The math ruled out an extragalactic origin entirely. All 12 of these powerful sources had to reside inside our own Milky Way. That single realization did two things at once. It confirmed that the knee in the energy spectrum had nothing whatsoever to do with cosmic rays arriving from other galaxies, and it brought the entire search dramatically closer to home. The race to identify these pevatrons was on. Before El Hasso began rewriting the record books, astrophysicists had spent decades building theoretical frameworks about what kinds of objects might be responsible for cosmic ray production. Space, after all, is a bizarre and spectacular place, populated by objects exhibiting behavior so extreme it strains credulity. But which of these extreme environments could genuinely generate the highest energy particles? and through what physical mechanism? For the past 7 decades, one leading hypothesis pointed squarely at supernova remnants. The energetics certainly seemed right. Theoretical calculations showed that if supernova remnants converted just 10 to 20% of their kinetic energy into particle acceleration, they could account for the bulk of cosmic rays observed within our galaxy. Here's the mechanism at work. When a massive star detonates as a supernova, it launches material outward into interstellar space at tremendous velocity, driving a collisionless shockwave ahead of it, a boundary zone where density, pressure, and magnetic field strength all change sharply and abruptly. Any charged particle encountering this shock front gets ricocheted back and forth across the boundary, picking up energy with every single crossing. Particles can remain trapped within this acceleration zone for thousands of years, and the longer they stay, the higher their energy climbs. This mechanism is called diffusive shock acceleration, or the Fermi mechanism. But despite their theoretical promise, reaching peta-electron volt energies remains challenging for supernova remnants. Current models suggest that only during the first century of a remnant's life does its shockwave move fast enough to push particles to these extremes. Every known supernova remnant is considerably older than that. There is, however, one scenario where supernova remnants can still contribute indirectly to ultra-high energy gamma-ray production. If accelerated particles within the remnant gain enough energy to break free of the confining magnetic field, they can escape and become trapped inside nearby giant molecular clouds. Buried within this dense interstellar gas, those particles interact with the surrounding material and produce gamma rays that can reach 1 quadrillion electron volts, even long after the remnant itself has lost its capacity to accelerate particles that energetically. So supernova remnants retain genuine potential as cosmic ray factories. As many as 6 of El Chaso's 12 candidate pevatrons might be associated with them. But they are not the primary player scientists now believe we should be focused on. A different class of object can push energies even higher. Enter pulsars. If you've followed this channel before, you'll have some background on pulsars already, but here's a concise overview. Pulsars are rapidly spinning, intensely magnetized neutron stars born in supernova explosions. We've now cataloged over 1/500 of them. How do they generate such extreme gamma-ray energies? Pulsars already have a proven track record of accelerating electrons and positrons. The combination of a densely compressed rotating structure and an immensely powerful magnetic field generates enormous electric fields at the star's surface. These fields are strong enough to strip electrons directly off the star, launching them outward in a ferocious particle wind. When that wind eventually slams into surrounding material, such as the gas and dust of a nebula, it decelerates sharply, creating what is called a termination shock. At that shock boundary, the deceleration energy is transferred to the particles, catapulting them to extreme energies. A useful analogy is water flowing in a stream. Under normal conditions, the flow is smooth and orderly, but place a rock in its path, and the water that spills around the obstacle moves considerably faster. The El Chaso team estimated that over 30% of their candidate pevatrons could be associated with pulsars, positioning them as central figures in the search for cosmic ray origins. A third class of cosmic ray source caught scientists almost completely off guard. Returning to the energy spectrum and zooming into the region around the knee, what appears is not a clean, smooth curve, but a distinct bump, an anomaly sitting on top. The properties of the cosmic rays contributing to that anomaly simply didn't match either supernova remnants or pulsars. Something else had to be responsible. That forced scientists to think beyond conventional source categories and explore alternative, less familiar particle acceleration scenarios. And in doing so, they arrived at what may well be nature's most extreme particle accelerators: black holes. The proposition that black holes could generate ultra-high energy particles had actually circulated as early as 2009, described as the Bonados-Silk-West effect, after the physicists who formulated it. The framework describes a scenario in which two particles approaching a black hole from different trajectories collide in the extreme gravitational environment near the event horizon, potentially reaching energies with virtually no upper bound. For a time, however, this theory was considered practically useless because the particles would almost certainly be swallowed by the black hole before they could escape and do anything useful. That conclusion changed when more refined models showed that a meaningful fraction of these particles would, in reality, be flung outward rather than inward, escaping the gravitational grip entirely. Once free, those particles would propagate through the galaxy as none other than cosmic rays. We've walked through the theoretical landscape, but the real question is, what have we actually found out there? This part of the story demands honesty about difficulty. El Chaso may have pinpointed 12 candidate pevatrons within the galaxy, but identifying the actual astrophysical object responsible for each signal is an entirely separate and formidable challenge. Even so, the search is producing results, and a handful of specific sources have been confirmed. So let's take a closer look at them. The first confirmed object may already be familiar to you. The Crab Nebula, catalogued as Messier 1, is a supernova remnant sitting approximately 6,500 light-years away in the constellation Taurus. Breathtaking in appearance, Messier 1 is far more than an aesthetic wonder. It's a confirmed accelerator of electrons to energies of 1 quadrillion electron volts. As perhaps the most exhaustively studied object in the known universe, Messier 1 gives astronomers invaluable insight into how nature builds and operates particle accelerators at these scales. In the gamma-ray band, Messier 1 displays striking variability. It produces intense, high-energy flares that can persist anywhere from a few hours to several days. With the conceptual framework of pevatrons now in hand, scientists recognize that these flares represented photons produced by electrons undergoing extreme acceleration. Exactly what drives that acceleration remains debated. The possibilities include diffusive shock acceleration at the boundary between the particle wind and the surrounding medium, energy released through the breaking and reconnection of magnetic field lines, or a more complex internal mechanism operating within the particle wind itself. At very high energies, electrons transfer a portion of their energy to ambient background photons, boosting them into the gamma-ray band where instruments can detect them. However, accelerating electrons is enormously challenging because they shed energy extremely rapidly. To produce gamma rays at 1 quadrillion electron volts, the electrons themselves must have carried several times that energy at the point of emission. This makes Messier 1's status as a pevatron unambiguous and its performance remarkable. There is, however, an important distinction. This has been demonstrated only for electrons, making Messier 1 what scientists classify as a leptonic accelerator. But pevatrons are capable of accelerating any charged particle. And since cosmic rays are composed predominantly of protons, it's hadronic pevatrons, those that accelerate protons and heavier ions, that researchers are most urgently pursuing. That 4-to-1. 4 peta, electron volt photon detected by LHASO, the highest energy photon ever recorded, sent scientists scrambling to identify its point of origin. That investigation led them to the next confirmed source, the Cygnus region. Cygnus is one of the most immediately recognizable constellations in the northern sky, stretching across more than 800 square degrees of sky, equivalent to some 4,000 full moons placed side by side. Within this rich stellar territory, scientists found something remarkable. LHASO detected an abundance of peta-electron volt photons concentrated within the Cygnus cocoon, a vast superbubble surrounding an intensely active region of massive star formation. At the heart of that superbubble sits a massive young stellar cluster known as the Cygnus OB2 Association, a powerhouse of stellar activity where the collective winds from dozens of hot, massive stars generate tremendous particle accelerating forces. Cygnus OB2 lies nearly 5,000 light-years from Earth, and its spatial position aligns well with the gamma-ray signals LHSO recorded. But as noted earlier, gamma-ray directions point towards sources without specifying how far away those sources actually are. In a region as energetically rich as Cygnus, multiple candidate objects occupy overlapping lines of sight, making source identification genuinely complicated. Roughly in the same direction as OB2, though at a considerably greater distance, lies an X-ray binary system called Cygnus X3. It consists of a donor star feeding material into a compact companion object, most likely a black hole or neutron star. The donor is a Wolf-Rayet star, meaning it is extraordinarily hot, massive, and luminous, and it funnels material toward the compact object through intense stellar winds. The compact object, in turn, fires powerful jets of plasma outward into space. Together, these components create near-ideal conditions for extreme particle acceleration. Initially, distinguishing which of these systems was responsible for the peta-electron volt signals LHASO detected seemed like an impossible task. But a careful examination of the signal itself revealed something deeply revealing. Hidden within the data was a temporal signature, a repeating pattern cycling every 8 hours, visible not just in the gamma-ray emission, but in corresponding X-ray and infrared measurements as well. The source of that rhythmic pattern became clear upon further investigation. Every 8 hours, the compact object within Cygnus X3 completes one full orbit around its massive donor companion. That orbital period left an unmistakable imprint on everything the system radiated. Scientists could now state with certainty that the gamma rays were being produced by Cygnus X3, confirming it as another confirmed pevatron. Cygnus X3 turned out to be a particularly fascinating object to study. The highest energy photons detected from the system already registered at 7 peta-electron volts. Since those photons are produced by accelerated protons, the protons themselves must have carried several times that energy at the moment of interaction. That calculation implies that Cygnus X3 is not merely a pevatron, but a superpevatron, capable of pushing protons beyond 10 peta-electron volts. We've raced through some of the most electrifying pevatrons identified so far. But where does this field go from here, and what new horizons might the search uncover? Hunting 12. The candidate pevatrons already sounded like an ambitious undertaking, but the numbers since El Hasso's initial findings have exploded. In 2023, El Hasso published the first comprehensive global catalog of galactic pevatrons, documenting 43 ultra-high energy gamma-ray sources. Now, just 2 years later, with sustained monitoring from observatories operating across multiple continents, that catalog has grown to more than 75 confirmed candidates. With that many potential pevatrons embedded within our galaxy, we are overdue for a fundamental reassessment of what the Milky Way actually is. For a long time, astronomers considered our galaxy relatively quiet, lacking the colossal black holes associated with galaxies that have undergone violent, energetically explosive histories. El Hasso's body of work has rendered that characterization obsolete, reshaping our picture of the non-thermal universe beginning with the galaxy we call home. The era of pevatron hunting has never been more dynamic. El Hasso is operating in collaboration with multiple high-energy gamma-ray observatories spanning the United States, Germany, Namibia, and Spain. This global scientific network has cultivated an open and genuinely collaborative research culture, with institutions sharing data freely and pooling evidence to build the strongest possible case. Their collective ambition is to construct a complete photon energy spectrum across all observable energy bands, while simultaneously measuring X-ray and gamma-ray emissions from instruments above Earth's atmosphere. I want to extend my sincere gratitude to Professor Cao for his generosity and expertise in illuminating this corner of high-energy astrophysics. As everything we've seen today makes plain, the study of pevatrons is one of the most rapidly evolving frontiers in modern science, and observatories like El Hasso are its beating heart.